Good morning, everyone, and welcome back to our third day of our meeting. Our first talk will be given by Antony Rangachev from University of Chicago, and he's going to talk about generalized smoothability. Thank you very much.
Well, thank you very much for the invitation to speak here. It's always a pleasure to be in Brazil and at IMPA. Today I will talk about generalized smoothability, and pretty much everything mentioned in my talk is part of the preprint, my preprint local volumes, equisingularity and generalized smoothability. So all the proofs and statements of the theorems can be found there. I don't have to introduce to this audience the subject of smoothability. For a given algebraic variety, the existence of a smoothing is central to the study of its geometry and topology. And today I'm going to propose a notion that can be used for the cases when such a smoothing does not exist. And I'll argue that this is equally good in many situations. Okay, so before going to the notion of generalized smoothability, let me quickly review what's known about smoothability. So we can trace the origins of the subject due to Severi, who postulated that any algebraic variety is a limit of smooth algebraic varieties. Okay, so let's write it informally in this way. Severi was interested in curves, and he had hypotheses on this, what we call now nearby fibers. So he would say that the degree of the embedding of these curves and their arithmetic genus are constant, and which in modern language translates to insisting that X can be realized as, the generation of smooth varieties. Or the XTs for generic T are smoothing of X. Okay? This turned out to be inaccurate. Well, there were lots of counterexamples given during the years. The first one is due to Tom from 1957. So Tom showed that the affine cone of the Segre embedding of P1 cross P2 in P5 is not smoothable. He had a topological argument for this, and Wey was the one who, in fact, showed that this is this affine cone over the Segre embedding of P1 cross P2 in P5 is rigid. So this is four-dimensional example of a non-smoothable singularity. Finding non-smoothable singularities in high dimensions is easy. In fact, one can proceed with these affine cones, so one can consider so one can look at PA cross PB and prove that the affine cone over this is non-smoothable. But finding smaller dimensional non-smoothable algebraic varieties is not that easy. It took some time. So the first, I think the first non-smoothable surface singularities were given by Mumford and Pinkham. non-smoothable surface singularities. We have examples of non-smoothable curves, monomial curves, so by Book-Weitz. Non-smoothable monomial curves. And we can go further down. There are examples of non-smoothable zero-dimensional schemes by Rubino, but yeah, don't want to discuss this case now. And on the positive side, we have that complete intersections are smoothable, and this is an easy application of Sartre's theorem. So complete intersections are smoothable. So if we try to look for other examples of smoothable singularities, a natural class to consider is the class of determinantal singularities. So what's known in this case is that, so if X is determinantal, and it's well, given by, assume that it's given by the T by T minors of a R by S matrix. Then X is smoothable if the dimension of X is less than R plus S minus 2T plus 3. Okay, so this result is due to Wall. So in particular, so we have one important class of determinantal singularities, and this is the class of Cohen-Macaulay codimension 2 singularities. So in particular, if X is Cohen-Macaulay codimension 2, then X is smoothable if the dimension of X is at most 3. So this is due to Schaps. So one can show that if one goes, well, dimension 4, we have Tom's example. This affine cone over P1 cross P2 in P5 is realized as the 2 by 2 minors of the generic 2 by 3 matrix. Okay? So this is the first example of a non-smoothable Cohen-Macaulay codimension 2 singularity. And once you go dimension 4 and higher, X, and if X is Cohen-Macaulay codimension 2, then X is not smoothable unless it's X is a complete intersection. So this is kind of best possible. So there is another important class of singularities. So So this is the class of Pfaffian singularities, so X Pfaffian. So X is given by the 2m by 2m Pfaffians of a 2m plus 1 times 2m plus 1 skew-symmetric matrix. Then X is smoothable if the dimension of X is less than or equal than 4 times n minus m plus 6. So this is again a result due to Wall. So there is an important subclass here, and that's the subclass of Gorenstein codimension 3 singularity. So in particular, if X is Gorenstein codimension 3, and the dimension of X is at most 6, then X is mutable. Okay. So this is a brief summary of what we know about smoothability. And now I would like to talk about this notion that generalizes the usual smoothability that we are aware of. So how do we measure singularities? Well, there are various ways to do that. And the most naive way to do it is through tangent spaces. In equisingularity theory, it was understood by the work of Tessier and Gaffney that, and others, that it's advantageous to look at conormal spaces, not at just tangent spaces or Nash modifications. So I'm going to talk about conormal spaces now, and Terry talked about conormal spaces in his talk, and I'll briefly review the definition of a conormal space. So conormal spaces. So suppose X is complex analytic in Cn, so the conormal space X prime, of the conormal space of X prime is defined as the closure of O pairs. So X is a smooth point, and H sub X is a tangent hyperplane. It's a hyperplane in Cn that contains the tangent space at the point X. Okay, so this is defined on the smooth locus, and we take the closure of this, the Zariski closure of it. So of course I have to say that X prime is reduced. And yeah, this is in X prime cross Pn minus 1. We can projectivize, and so this sits in X prime cross Pn minus 1. Wow. Dual. Okay, so here I have a structure morphism from Cx prime, from the conormal of X prime to X prime, and now denoted by C. So now let's fix a point. So let's fix a point x prime in here, in capital X prime. And I'm interested at the fiber of the conormal over that point. Okay? So I'm interested at this fiber So what we know is that its codimension is at most the dimension of x prime and is at least 1. So here let me in fact write it down. So x prime is reduced, and I'll further assume, in order to make sense of this codimension, to make sure that the codimension is well behaved, I will assume that x prime is equidimensional. Okay. Pure dimension. So this is what we know about the codimension. This is all standard. So the situation where the codimension of this fiber is equal to the dimension of x prime. In many cases, it implies that x prime is smooth. And if you are in the case when the codimension of this fiber is 1, in other words, this fiber is big, you should expect to be over a singular point. So here is a result due to Gaffney and Massey. So if x prime is a complete intersection, such that x prime is smooth away from, well, capital X prime is smooth away from the point x prime, and such that the codimension of this fiber is at least 2, then x prime is a smooth point. Of capital X prime. So, well, the way they phrase it was in a different way. So they said that if you have an isolated complete intersection, then the fiber of the conormal over the singular point is of codimension 1. So I'm just rephrasing it in this way. So if you have that x prime is smooth away, capital X prime is smooth away from the point x prime, and if the codimension of this fiber is at least 2, then that point is smooth. Okay? So here is the notion that we need to introduce this idea of generalized smoothability. So we say that x prime is a deficient conormal singularity at the point x prime is deficient conormal singularity if the codimension of the fiber of the conormal over that point is at least 2. Okay. So the main question now that I want to study is which singularities deform to deficient conormal singularities. So by the way, I want to mention, this is an obvious remark here, that if x prime is smooth, and the dimension of x prime is at least 2, then x prime is a deficient conormal singularity. And I will abbreviate this deficient conormal by DC. It's a DC singularity in each of its points. Okay, so this is standard because the conormal in this case is a bundle, and each of its fibers, it's of codimension, at least the dimension of the underlying space. And if the dimension of the underlying space is at least 2, then each of its fibers is of codimension at least 2. Okay? So now the question I want to study, so main question, so start with an isolated singularity in Cn. So I want to find out which, so this is an isolated singularity. So I want to find out which isolated singularities deform, and by deform here I mean embedded deformation, to an isolated singularity that's deficient conormal. DC singularity. So which X admit such deformations? So, of course, this class, again, let me remark trivially, and this follows from this remark here, that this class contains all smoothable singularities. So this is trivial. So this class, so all smoothable singularities of dimension at least 2. So if X is smoothable and the dimension of X is at least 2, then X belongs to this class. Then X deforms to this C singularity. So this is trivial. Now, in order for this class to be meaningful, one needs to come up with lots of examples beyond the class of smoothable singularities. So here I'm going to list a few results in this direction, and then at the end I'll give an idea of how the proof goes. So in this talk, I don't have the time to elaborate on why this notion of generalized smoothability turns out to be very advantageous if one wants to study equisingularity. Why this is good enough, as good as, so the existence of such deformations, why is it as good as the existence of a smoothing? Yeah, so, well, this is in my preprint. So in this talk, I have only the time to tell you a bit about what's known about this class. So let me now say which classes admit such deformations, which classes of singularities are beyond the class of smoothable singularities. So determinantal singularities are in this class, and this is a joint result with Gaffney. So this is with Gaffney. Pfaffian singularities are in this class. So this is a computation that is based on the computation of the conormal spaces of the generic Pfaffian singularity, and this is a computation done recently by Lakshmi Bai and Singh. So based on a computation, so Pfaffian singularity is deformed to DC singularity, so this is based on computation of Lakshmi Bai and Singh. And already these two classes are interesting in the sense that they reveal that this class is much larger than the class of smoothable singularities, because as we saw, determinantal and Pfaffian singularities are smoothable only in small dimension, and in large dimensions they are smoothable if they are of specific type, like complete intersections. But in general, in large dimension, for each dimension, there's plenty of non-smoothable singularities, both determinantal and Pfaffian. And so what's next? So, well, here I was not very accurate. So determinantal singularities are smoothable. There is one exception. There is one exception, and this is the case of those determinantal singularities that are given by the 2x2 minors of a square matrix, or geometrically. Okay, so these are, so in the notation that I used before, so this is the case of a square matrix, 2x2 minors, or this correspond to the affine cones over the Segre embedding of PR minus 1 cross PR minus 1. So affine, yeah. So those are not deficient conormal. So that's the only exception. Okay, and so for some time I had the conjecture that perhaps this class of singularities has a significant overlap with the class of Gorenstein singularities. But I'm not so sure how accurate this conjecture is anymore, because these turn out to be Gorenstein. And you can, of course, by varying R, you can get an example of a Gorenstein singularity in each even dimension, which is not in this class. So very recently, I understood that the right point of view is to study this through linkage theory. So let me briefly say what that is. So L0, let's say that L0 is the class of complete intersections. L1 is the class of these varieties such that their union with complete intersection is complete intersection. L2 is the class of these varieties such that their union with varieties from the class of L1 is complete intersection, and so on. So there is an algebraic theory of linkage by Shapiro and Peskin and by Huneke and Ulrich that describes the equation of those. So two examples from the list above that are in this class, that are in some of these, that correspond to some of these links here, are the class of Cohen-Macaulay codimension 2 singularities and the class of Gorenstein codimension 3. They can be realized through the theory of linkage. And so those, so this is a recent result with Ulrich. So it's still work in progress. So these are deformed to DC singularities. Okay. So let's see, how much time do I have? 10 minutes. Okay. So what is the idea of the proof? How does one proceed? Well, all these classes can be realized in the following way. So suppose G is a holomorphic map between affine spaces. So here X is a subvariety of, is a variety in Cn, V is in Cm, and X is G inverse V. So X is G inverse V. So this is the setup that I'm describing is applicable to all these classes. I will illustrate this setup just for the determinantal singularities. So X is G inverse V. Codimension of X is equal to the codimension of V. And I will assume that X and V are irreducible. So how do we realize determinantal singularities? So for the determinantal case, let me here just remark here, for the determinantal case, so you take Cm to be the space of matrices, CR, R by S matrices, and you take V to be the space of matrices of rank at most T. Okay? And then each determinantal singularity given by T minors of an R by S matrix is realized in this way. This G corresponds to specializing the entries of the matrix to some polynomial functions. Okay? And this V is the generic such determinantal variety. And so here, so we think of the entries of the matrix as like well, each entry is a variable, and V is given by the T minors. Specific X, we specialize the entries of this matrix. Okay, so the first observation we need is that if G is transverse at the origin at 0, so at V at 0, and if V is a deficient conormal singularity at 0, then so is X. By transverse at 0, I mean that one takes a Whitney stratification of V, and this transversality condition is that G is transverse at the stratum that contains the origin. So this is the first observation that we need, and this is more or less follows from using some Lagrangian geometry. I don't have an algebraic proof yet, so this really works only over the complex or the real numbers. The second result is a result due to Buchweitz. So additionally here, I will assume that V is Cohen-Macaulay. So then Buchweitz tells us that any unfolding capital G of G, so unfolding gives a flat deformation of X. So this curly X, which is the inverse image of V, this family is a flat deformation. So just by perturbing the entries of G, we get a flat deformation of X. Okay? So this is a homological result due to Buchweitz. And finally, what one needs is a version of Thom's transversality in the complex analytic case, which is due to Trivedi. So I'll phrase it in the following way. So G can be chosen so that the generic fiber of this map is transverse at the origin at V. So you see, when you start with a determinantal singularity, this map usually is not going to be transverse at the origin of V. So what this machinery tells us is that by perturbing the entries of G, first we get a flat deformation of X. Second, by Thom's transversality, we can ensure that the fibers, the generic fibers of this map, are transverse at the origin at V. And then third, by this result that I mentioned there, because of this transversality, if V is deficient conormal, then the generic fiber of curly X will be deficient conormal. So let me write this down. So then if V is a deficient conormal singularity, XU, so U generic, which is equal to the inverse image of the generic fiber of G at U, is a deficient conormal singularity. So using these three steps, one reduces the problem to computing the conormal spaces of the generic singularities. In the case of determinantal singularities, these are the generic determinantal singularities. This we did with Terry. In the case of Pfaffian singularities, this was done by Lakshmibai and Singh, who did use representation theory to compute these conormal spaces. And in the case with Ulrich, we have a way, in the case of these varieties that belongs to these linkage classes, we have a way to compute the conormal spaces of the complete intersections that participate in each one of these generic links that I listed on the board. So this is the idea of the proof. Thank you.